Hello everyone, welcome to Math Advice. In this video, let me see an example in a complex form of Fourier series. Here I am going to take the function f of x equal to sin x in an interval 0 to pi. Find the complex form of the Fourier series f of x equal to sin x given in an interval 0 less than x less than pi. Okay. Now, I have just shown you the formula table for your reference. Here under pi form we are having three types of intervals, that is minus pi to pi and 0 to 2 pi and 0 to pi. So given problem is under the third category, that is half range. Isn't it? 0 to pi. If it is so, the general form of Fourier's complex Fourier series of the form f of x equals sigma n raised to minus into to infinity cn e power I 2 and x. Where cn is calculated by making use of the formula 1 over pi into 0 to pi f of x e power minus I 2 n x dx. Okay. So let me take down the formula for 0 to pi. This is a general complex Fourier series. For that we make use of the formula Cn. This one for calculating the value of Cn. First let me calculate the value of Cn, and substituting in f of x gives you the complex Fourier series representation of the given function f of x equal to sin x defined in interval 0 to pi. So Cn is equal to 1 over pi times 0 to pi f of x equal minus I 2 n x dx. Now, in your next step, 1 upon pi integral 0 to pi. Here, your f of x. What is your f of x? Your f of x is sin x, isn't it? Sin x e power minus I 2 n x dx. So, that is equal to, what I am going to do, I am just interchanging the quotient. So, interchanging the quotient doesn't change the value of the interval, because these two of them are in terms of multiplication, isn't it? So I am going to take e power minus I 2 and x as my first term, and sin x as my next term dx. So this is of the form you know already, integral e power ax sin bx dx, isn't it? So you know the formula already. E power x sin bx dx is nothing but e power x divided by a square plus b square of a sin bx minus b cos bx. That's all. So what is your a? So in our problem your a is nothing but x coefficient. Your x coefficient is nothing but minus I 2n, and b is equal to sin ax. Sorry, sin bx. So b is nothing but 1. Okay. So substituting the formula. So by taking a is equal to minus I 2n, b is equal to 1, here you get 1 upon pi of e power minus I 2n x over a square, that is minus I 2n the whole square plus b square is 1 square of a. What is your a? Minus I 2n sin bx. B is 1, so you just write sin x, minus b. B is nothing but 1 cos bx. B is 1, so 1x, that is nothing but x itself. So with the limit from 0 to pi. Look at here. So you know the values of I square. Squaring this you get I square is minus 1 and minus square is nothing but plus, isn't it? So you get the denominator. So 4n square, that is minus, right? So I square become minus 1, so minus become positive. So minus 4n square plus 1 square is nothing but 1 itself. So my next step I am just squaring the denominator down and write down the remaining term as it is. So Cn is equal to 1 upon pi. Look at here. I am just writing the remaining terms as it is. Only I am just squaring the denominator alone. Okay. So of e power minus I 2 and x over minus 4n square plus 1 of, within bracket here you have minus I 2n sin x minus cos x. Okay, minus I 2n sin x minus cos x with the limit from 0 to pi. So what I am going to do, I am just taking this outside because the limit is only for these 6 terms. Okay, so that's a constant. So if you take it outside, it's 1 by pi of, and just write minus 4n square plus 1 as 1 minus 4n square. Both are equal, isn't it? So of e power minus I 2 and x of minus I 2 and sin x minus cos x with the limit from 0 to pi. So as usual, upper limit minus lower limit. So 1 upon pi of 1 minus 4n square of, first let me replace these x by pi. If you replace x by pi, what you get? E power minus I 2 and pi of minus I 2 and sin pi minus cos pi. So upper limit over, close the parenthesis, minus. Coming to the lower limit, so if you replace the value of e power 0, e power 0, you know the value of e power 0 is 1. So first term, since the value of e power 0 is 1, so e power 0, 1 product, and also the value of sin 0 is also 0, cos 0 value 1. So if we replace this x by 0, sin 0 is 0, minus cos 0 value is 1, that's all. So upper limit minus, coming to the lower limit, this is your lower limit, okay, close the bracket. Now, the next step what we have to do is, you know the value of sin pi value is 0, so this term becomes 0, and the value of cos pi is nothing but minus 1, okay. Simplifying this, you get Cn is equal to 1 upon pi of 1 minus 4n square. So within the bracket you have, look at here, so for this you have e power minus 2n pi, this term becomes 0, so here you have minus 1, so minus, these two minus become positive, okay, so plus 1, right, so 0 plus 1, so e power minus I 2 and pi of first term becomes 0, the second term we have plus 1, okay. So upper limit over, minus. Coming to the lower limit, so here you have 1 product minus 1, 1 product minus 1 is nothing but minus 1 itself, so minus 1, that's all. So simplifying this, you get 1 upon pi of 1 minus 4n square of e power minus I 2n pi plus 1, isn't it? Minus and minus becomes plus. So by expanding this, so you know what is e power minus I theta, that is pi minus I sin 2n pi plus 1. You know the value of cos 2n pi, cos 2n pi value is plus 1, sin 2n pi value is 0. So simplifying this, you get 1 upon pi of 1 minus 4n square of 1 plus 1. That is nothing but 2, isn't it? So that is equal to 2 divided by pi of 1 minus 4n square. So this is the value of Cn we have calculated, and substituting in f of x, that is your general complex Fourier series of the form f of x is equal to sigma n varies from minus infinity to infinity. The formula we have used is Cn e power I 2n x. So substituting the value of Cn here, n is equal to minus infinity to infinity. The Cn value we have calculated just now is 2 upon pi of 1 minus 4n square e power I 2 and x. Here 2 and pi are constant, so you take it outside of the summation. So 2 by pi sigma n varies from minus infinity to infinity e power I 2 and x upon 1 minus 4n square. So this is a complex form of the Fourier series of the given function f of x is equal to sin x given in interval 0 to 1. So this is the complex form of the Fourier series representation of the given function. So up to this, hope you got a clear idea about how to find the complex form of the Fourier series. Okay, thanks for watching. See you all again in the next video.